So that, if you're not familiar with it, is a simulated virtual trip to the Southern African Large Telescope, which is actually a twin to the largest optical telescope in the world, although big is not always better. It is very, very big, and I'll say a little bit more about that in a while. All right, let's just get out of here. And I should say I'm always ranting on about how I think that lectures are a terrible way of trying to get information across to people. Okay? But here I am giving a lecture. So please just when I... Oh, let's get rid of this. We can do with that. Okay. I'll come back to it in a while. Let's get this up. Okay, so when I do stop and suggest that you think about something, there probably won't be all that difficult things to think about. It's worth your while just to, tune back in, have a thought. The talk is, I knew there was going to be a huge range of people in the audience, so there's some real beginner things, and there may be some things that you haven't heard, even if you're quite far along. So just keep tuning back in to see if there's something new for you. Okay. All right, so I'm talking about astronomy and astrophysics, and I like to claim that with astronomy, you can say something about fundamental physics. And just as a quick example of that, I'm going to show you the evidence for dark matter in the universe. So either we're going to, just from looking at these few bits of evidence, we're going to either conclude that there's something wrong with our theory of gravity, or there is a lot of matter in the universe which is nothing like the stuff that we have. Okay? So that's pretty fundamental, right? If it's really one of those two things, that's pretty fundamental. So the thing is, often astronomy is a bit of a bad name because the observations are really messy. And so you get this kind of messy astronomy observations implying something rather fundamental. Okay? And for those of you who have a different take on fundamental physics doing fundamental physics in general, I'd just like to point out that fundamental physics leads to new technology and economic growth. Now, most physicists just accept that. And I'm not sure that that is really happening in South Africa, and it's something maybe we should think more about. Okay? Just a note about the growth of astrophysics worldwide. If I look in physics today, 20% of the jobs are for astrophysicists. Okay? And you look around in South Africa, or I guess in Africa in general, you don't see those kinds of numbers reflected. Is anyone in the audience who can do anything about that? No. All right. And we had 11 Nobel Prizes in the last 30 years. So South Africa is positioning itself to really focus on astronomy. Okay, we're building, like I said, a twin of the largest optical telescope in the world, which will be online at the end of this year. We're bidding to host a $1 billion radio telescope, and we have the high-energy stereoscopic system. Okay, so there's a lot of support for this, and this is part of the astronomy business. In South Africa, we have great skies and great skies to sell, and people are buying. So actually, it's really much more money coming into South Africa for astronomy than is going out. So that's a good reason for doing it, even if you don't want to do fundamental physics. And I should just point out that the NRF has identified astronomy as one of the 6 areas where we have a distinct South African research opportunity because of our geographical position. Okay, that's in all of science, social science, everything. 6 areas where they've said this is where they want us to focus. Okay, and that's not to say that we can't do fundamental physics. Of course, I think fundamental physics fits in very nicely with that. Okay, so let me just remind you about the multi-wavelength universe. Okay. We've got the electromagnetic spectrum. We've got SALT, which will go online at the end of the year. HESS, looking at the sort of 100 GeV and higher range. We're bidding to host the square kilometer array. And I should point out that the astronomers, amazing collection of people, because they let their data go public about a year after it has been taken. Okay? So in the US, they'll spend $1 billion launching a big telescope. And a year later, after the observations are taken, you can access that data you sitting anywhere in the world, your government didn't have to put any money in, and you have access to this extraordinary data. Okay? So that's great. We actually have access to this whole wavelength range to explore the universe with. Okay? Said first light in 2004. Okay? It's a 100 million rand project. There's Hess. So that the way that works is you have these very, very high energy particles coming into the atmosphere, and they emit Cherenkov light. Okay, so it's actually a sort of optical telescope picking up the optical light that comes from when the high energy particles come into the atmosphere. That's a radio telescope at the moment, and we've just had the Square Kilometre Array Steering Committee in Cape Town during this last week. Busy trying to sell South Africa as the site to put this. That's a $1 billion project, which will probably be built in about 2010, and we're kind of second in line behind Australia for this really great project. So that's sort of South Africa's position. There are not that many local speakers in this thing, so I thought I should give a bit of a South Africa slant or Africa slant on the proceedings. So let me just remind you, I've spoken to some of you, so I know some of you have never done any astronomy at all. So I'm sorry for those of you who saw this in grade 4 or whatever. The Earth is about 10 to the 4 kilometers across. The Sun is about 100 times bigger, with that little blue dot up there is the Earth. Okay? Then we go out 4 orders of magnitude, and in the middle here we just have the 4 inner planets going around the Sun very quickly, and these outer planets going around really slowly. I'll need those ideas about going quickly and slowly later on. That's just Keplerian, right? If you look at if most of the mass is at the center here, then you expect the velocities of these things to decrease as sort of 1 over square root of r as you move away in r from the center of the Sun, because the Sun completely dominates the mass of this system. Jupiter's only about 1,000th of the mass. Okay, then we go out 8 orders of magnitude to get the whole galaxy in. Okay, so our Sun is just one of 100 billion stars in the galaxy. Okay, just quite an ordinary kind of star, our Sun is, and it would be sitting somewhere out in the. If this were our galaxy, of course, we can't take a picture of it from a distance because we're inside, but we would be sitting in. It would be a sort of bulgy region in the center, and then a disky region stretching out like this. Bulgy region in the center, disky region stretching out. We'd be somewhere out here, the Sun. And if I look face on onto there, it looks like I've drawn it a sort of spiral shape. Okay, there's that galaxy again. We move out. Okay, another factor of 100. And here what you see are clusters. This is a cluster of galaxies in the foreground. You probably wouldn't be able to immediately pick out the things from the foreground, from the background, but these things are all foreground galaxies, so each with their 100 billion stars, okay, 100 billion suns. And then there's some background galaxies in this picture, these long stretched things, okay, and those are actually gravitationally lensed. So I'll talk more about gravitational lensing, because that's a very useful way of saying that we really have strong evidence for dark matter. Then if you move out even further, we get to large-scale structure. So with this, you should be picturing yourself down here, and you're looking out into space like this, and we've just plotted the positions of the galaxies. You see that they're quite clustered. Okay, it's not just homogeneously distributed, they're quite clustered. So that's important, because ultimately, when you do cosmology, you'd like to be able to run the clustering of things all the way back in time and infer information about the density fluctuations in the early universe, because that puts constraints on your particle physics theories. Okay? It's quite a long way around, actually. I'll show you a much easier way to get to the early universe. All right, once again, some rather introductory stuff. Here I've plotted just taking the brightness of the stars, brightness of stars, and plotted them against their temperature in this annoying astronomy fashion. There's high temperatures at this side and low temperatures at that side. Okay? And so you see that most stars sit along what's called the main sequence here. Okay, so the physics that controls that is just all very easily well-known physics: hydrostatic equilibrium, gas, and nuclear fusion going on at the center of stars. So that's not interesting to people doing fundamental physics. We understand all of this. We know how stars evolve, from my point of view anyway. There are a few little details which we could figure out. But okay, so there's the main sequence. Then generally stars move off the main sequence, become giants or supergiants. Okay, so they swell up. Then something like our sun, okay, sheds out its outer layers and travels around here, and its core becomes a white dwarf, and it loses its outer shell. Okay? So these are just words I wanted to mention later. You should just remember white dwarf, main sequence, giants. So just showing you the evolution here. The sun collapses onto the main sequence, sits there for about 10 to the 10 years, evolves, becomes a white dwarf. Okay, and I'll show you the nucleosynthesis in a second. Okay, a more massive star will go higher up here, so it'll have a higher temperature, a higher luminosity, burns brighter, burns quicker. Okay, becomes a giant very quickly, and I'll show you the nucleosynthesis, but it becomes a supernova, so the whole thing explodes. Okay, so you should always have in mind that a low mass star sort of becomes a white dwarf, and a high mass star produces a supernova, and at the center it can produce a neutron star or a black hole. Okay, now I'm only just doing this nucleosynthesis thing because it was a place where people looked at stars and predicted something about nuclear physics just from looking at stars. Okay, so yeah, I'm not going to go into all the details, but basically you turn hydrogen into helium at the center of the star while it's on the main sequence. You use up the hydrogen at the center, and you start burning hydrogen in a shell. You come down here. Eventually, the helium can get ignited and starts producing carbon. Now, we knew that eventually we'd produce these carbon-oxygen white dwarfs at the center and lose our mass. Okay, so you have the carbon-oxygen. We wanted to produce carbon and oxygen at the center of the stars, and for that you need 4 alpha particles, 4 helium nuclei to come together. And so, I should have Linux problems. Beryllium, gamma, and an alpha particle. And to make carbon, but it had to be predicted that you would actually have this excited state of the carbon nucleus, which was just right for tunneling. Okay, otherwise you wouldn't make this reaction wouldn't go quick enough, and you wouldn't make nearly enough carbon. Okay, so this was something that a theorist just sitting back they had their star data, and they figured out, okay, there must be an excited state of the carbon nucleus, right? Otherwise, we wouldn't be able to produce the carbon and oxygen in the core of a star. So the nuclear physicists went and looked for this, and sure enough, found that. Okay, that's just an example of how you can use astrophysics to do something a bit more fundamental. And at that time, that sort of nuclear physics was kind of fundamental. Maybe not anymore. Okay. So, yeah, we probably aren't interested in the details of what happens after that. I should just say, in supernova, you can get other kinds of nuclear processes happening. This was all for the nuclear physics people. I'll talk much more about Big Bang nucleosynthesis in a minute. So that was where I was actually going to start a talk, but I realized that a lot of the words on there, maybe people wouldn't know. So this is actually a very hot area in astrophysics at the moment, is looking at extrasolar planets, but I don't really see any fundamental physics applications there, but it's very interesting to think about how life might evolve in other solar systems. So although that's not all that fundamental physics, that's actually a very interesting growth area. Stars, people doing fundamental physics like to look at neutron stars because they're very extreme environments, okay, and the gravitational wave implications. But otherwise, I don't think there's anything all that interesting there for the fundamental physics people. Galaxies, well, I'll show you in a minute that our evidence for dark matter comes from galaxies. And once again, either you need to have a whole bunch of very strange matter in the universe, which is important for fundamental physics, or something wrong with gravity. Okay, so that's the structure and dynamics of galaxies. That's important. Active galactic nuclei, that's where you have big black holes at the center of galaxies. So that's also a very extreme environment, interesting for people doing, anything to do with black holes. Okay, galaxy formation and evolution, I've put in quite a lot of effort there, because you need to understand how the luminous matter interacts with the dark matter to find out stuff about the dark matter. And like I said, with the large-scale structure, that was the picture I showed you, kind of looking out where you see that galaxies are clustered, and if you can run that through in time, the evolution of the clustering tells you something about the nature of the weird matter in the universe, and if you run it back far enough, it can tell you something about the initial conditions. Okay, and in cosmology, I'll talk about the cosmic microwave background, and these are just sort of fields that people look at in cosmology. I haven't picked them very carefully, but the only ones I'm really going to talk about are these two. I'm not going to talk about early universe physics. Okay, so here's, often I'll ask people will say, yes, but how do we know this stuff? How do we know that's what we're measuring? Okay, so of course it all comes down to spectra, and this is first year or high school for some of you. I'm sorry about that. But basically, if you have a black body and you take a spectrum of it, you get some nice continuous spectrum. If you put a cool cloud of gas here on this side of the black body, and then you spread it out, okay, then you'll get some absorption lines characteristic of whatever elements you have in your cool cloud. Okay, so that's an absorption line spectrum. And if you have some hot photons coming along here, knocking the electrons up to the higher energy levels, they recombine, then if you look at that cool cloud along that line of sight, you'll see some very specific emission lines, right? So, exercise number 1. What kind of spectrum would we expect from the sun? Or any star, for that matter? Well, we've got a star. It's kind of hot in the middle, cool on the outside, sort of black body in the middle, but cooler gas on the outside. Absorption spectrum, thank you. So that's what most stars look like. They have absorption spectra. Stellar spectra, okay, once more. Some basic stuff. Spectra give a surface temperature. Okay, so here I've plotted we have some spectra of stars. And you can see this one's a 3,000 Kelvin star, 6,000, 12,000. And as you move in that direction, as they get hotter, so the peak shifts and you get more and more emission at all temperatures. Here we've just got a whole bunch of emission line spectra for different elements, so sodium, hydrogen, calcium. There we've got a black body spectrum. And here would be maybe a spectrum of a star, right? So what kind of elements can you see? Hydrogen, some sodium, some iron. Okay, so you can run down and pick those out. And that's what people did in astronomy for decades, looking at spectra of stars, figuring out how hot they were, figuring out what chemical elements were in their atmospheres. And here's something important. How do you get the velocity of something from looking at a spectra? Because this is key, right? We have to measure velocities if we're going to get to the expansion of the universe idea. So here we've got something going around here, and at this point, the two emission lines will be at a certain wavelength, and you can see as it's moving away, so those wavelengths will get shifted to the red, and as it's moving towards you, so they get shifted towards the blue. Well, you can have a look at that for a bit. All right, so I want to measure the velocity of a galaxy. How am I going to do that? Well, go to a telescope, take the spectrum of a galaxy. What will the spectrum of a galaxy look like? Well, it's just made up of lots of stars, right? So it's just a superposition of lots of stars. So if we just look at this thing, stellar spectrum, okay? So we're just going to combine 10 to the 11 of those spectra on top of each other. Okay, and we get something that looks like that. So you can see that it's slightly smudged because all the stars are moving at slightly different velocities. But the big thing to notice is that the whole spectrum is shifted. Okay, there are those lines, and they shifted to the red wavelength. So they red shifted, and that's a Doppler effect, just like you saw from earlier. Okay. Yeah, I think don't even worry about that. The whole point is here that the spectrum will be red shifted in an amount that corresponds to the velocity of the galaxy, and so we can go and measure the velocities of galaxies. And what do we find? Well, we find that all galaxies are moving away from us. Okay, all galaxies are moving away from us. So what's your first thought? We're at the center of the universe and everything's moving away from us? Well, could be, but a much more likely explanation is this. Okay, that the space is expanding. So what you need to picture here is a little galaxy on, I wish we'd stop doing that for a second. Okay, so just on 2 grid points, picture 2 galaxies, all right? And now that thing's expanding, the space is expanding, so all the galaxies appear to be moving away from you. And what this is supposed to show you is that something with a specific wavelength will be going from blue to red, okay, as the space expands. So we can run that back in time and get some evidence for the Big Bang. I'm going to give you 3 bits of evidence for the Big Bang. I'm going to come back and talk a lot about the cosmic microwave background because this is where an enormous amount of interesting progress has happened. Breakthrough of the year, according to Science magazine last year, was observations of fluctuations in the microwave background. Okay, but here all I'm going to say is that early on in the universe, it was basically optically thick, so photons couldn't travel very far without bumping into something, knocking an electron up to a higher energy level, and photons being re-emitted, so they couldn't travel. Then the universe expanded, so then photons could travel, and in that process we went from having ionized hydrogen to recombined hydrogen, and of course some helium, which I'll mention in a minute. Okay, so that was the process about 300,000 years after the Big Bang, where suddenly photons started free streaming, and this was predicted in 1950. Okay, so don't chuck out the theorists. So if we look in any direction, okay, we look in that direction, look in that direction, you see the perfect black body. Okay, these photons streaming towards you from early times in the universe. Okay, so that's the second bit of evidence for the Big Bang. The universe was much hotter and very homogeneous. Okay, and the third thing is the Big Bang nucleosynthesis, and so we observe that 25% of the baryons in the universe is in helium. So that gives us evidence that the universe was originally much hotter and denser, like at the center of a star, where you burn up hydrogen to helium. Okay, so those are the 3 things, 3 bits of evidence for the Big Bang. Let me just remind you. Okay, if anyone challenges you on they don't believe in the Big Bang, they believe in something else, you say to them, how do you explain the cosmic microwave background, the Hubble expansion, and the Big Bang nucleosynthesis? Okay? Those are 3 things you should be able to snap out. How do you explain those? Because those are very strong bits of evidence. Okay, so let's have a look at the contents of the universe from a sort of astro point of view. We have baryons, and we have everything else in the standard model of particle physics. We don't bother to label them differently, electrons or anything. We just talk about baryons because they're more massive. We have dark matter. And now, we could have dark matter, and I'm going to give you evidence for dark matter. Could have dark matter which is either baryonic or non-baryonic. But I'm going to show you that there's evidence that it's non-baryonic. Okay? And by that we just mean matter with a normal gravitational interaction. And then we have this weird dark energy stuff, or cosmological constant, or lambda, and that has a very weird effect. The more there is, the more the space expands. Okay? And we usually just write it like this. In terms of the critical density, I'll say what critical density is in a minute. So we write omega. So if omega is 1, then you have critical density of something. So you could have critical density of baryons, which we don't seem to have, or matter, or cosmological constant type stuff. Okay. Are there questions about that at the moment? Yes. Yes, exactly. Okay. Before I go on, now more people have come into the room. How many of you were at George Ellis's lectures last week? Okay. So you're familiar with this then? Some people are. Okay, so these are Einstein's field equations. So typically what cosmologists do is they say, all right, let's make some assumptions about the universe. Okay, so what assumptions would they make? They're going to make some assumptions about the geometry, and they're going to put something in there. And they're going to make some assumptions about the matter-energy fields, and they're going to put it in there. Okay, and then you used to tack on this bit as a cosmological constant, but you can just as well think of that going in there. Okay. So what assumptions might we make about the geometry? And isotropy, homogeneity. We allow for some curvature, and it can be expanding. Okay, so once you make those assumptions, you get your Friedman-Robertson-Walker metric, okay, and that'll determine your G mu nu side of that equation. Okay, then you're going to think about what matter and energy is in the universe, and that determines your T mu nu for you. Okay, and you should have seen that we have a scale factor which basically describes the sort of average distance between galaxies. Will come out evolving something like this. Okay, so that's the change in the scale factor, that's the scale factor, and that's the energy density of the stuff. Okay, and that can be a combination of all of these things, which have different equations of state, like you say, okay, and so have different effects on the evolution of the scale factor. So you want to think back, are there more questions trying to connect this to something that you've maybe seen before? Okay. So if we're talking about the geometry, we can have a closed geometry. I think someone talked about this the other day, where we basically start out, if two light rays start out parallel in that space. Remember now, we're trying to represent the universe as a two-dimensional thing. So you start out with two parallel light beams, and if you're in a closed geometry, eventually those two things come together. Okay? If you're in an open geometry, the two parallel light beams diverge. Okay? If you're in a flat geometry, then they stay parallel all the time. And the example that was given by somebody was the sum of the angles. Okay? You can see that they don't all add up to 180 degrees. Okay, so, and that's just a sort of 2D representation of that. So that's, whatever's in the universe can determine that geometry, right? So you would have seen that before somewhere. And we can think about the future of the universe. I'm just going to ignore the cosmological constant for a second here. Okay, and we can think of a few scenarios. One is where there's not very much matter in the universe, so the universe has this intrinsic expansion, and it just, the matter can't keep it all together, so it just carries on expanding. So that would be an open universe. We can picture something that's got a whole lot of matter. It causes the universe to recollapse again. Don't worry about this. That's just wild speculation. Or we can, if we just got the simple model, we just have something will just recollapse again. Or we could have something in the middle where the expansion just goes to zero as you go off to infinity. Okay, and that would be a critical density universe. Remember, I told you measure densities in terms of critical. Okay, so we've got, assuming this kind of picture, we can say whatever stuff is in there is going to determine the future and the geometry. Okay. So now we're going to go and look and see what stuff we might find. So, evidence for dark matter. Who of you have seen this before? Rotation curves of galaxies as evidence for dark matter. Okay. Some vague thoughts about it. Ed, you took my class. Okay. Your hand was up. I'm sorry. All right, so we look out and we look at this galaxy here. This is actually the closest galaxy to us. I showed you, we're looking on, got the bulge, and now we're measuring how fast things are moving on either side of the galaxy here. Okay. So what we do is you start at the middle, measure velocities, and you can go all the way out beyond the stars, and you can do that by looking at just neutral hydrogen gas. Okay, so we can measure the velocity of hydrogen gas quite far beyond where all the stars are. Okay. Now, think back to the planet picture we saw right at the beginning. Okay. What was happening there? If this is the sun, okay, things near the sun were going around really quickly, and things out here were going really slowly, and that's because all the mass was concentrated at the center. Okay. Same thing with the galaxy. If all the mass is where the stars are, okay, all the mass is where the stars are, and you come out here and you measure the velocity of some gas cloud out here, what do you expect? You expect it to be going slower than the stuff in the middle, right? If all the mass is there where the stars are. So we don't see that. Okay? If this is 10 kiloparsecs out here, and here's the distance out to 10 kiloparsecs, and this is rotation velocity. You see it starts at the middle, it gets faster and faster. And here, at about 10 kiloparsecs, where you expect there to be no more mass, you expect a Keplerian drop-off, it just stays constant out there. Okay? So, what could that be? All right, let's stop for a minute and think about what it could be. Just from this evidence. Could it be a whole bunch of neutral hydrogen? From what I've shown you here, yes, it could be. Just very cold, not emitting light. So it's dark matter, which is baryonic, right? But I'm going to show you a bit of evidence just now, which says that it can't be baryonic. So there's dark matter, or there's something wrong with gravity. Okay? And at the moment, we think it could be baryonic. So we could come back and say, well, if it isn't baryonic, what else could it be? Do you have some slightly massive neutrinos? How about slightly massive neutrinos and a big haze around here? Well, yeah. You find, I think probably in the next lecture you'll find that I'll show you that neutrinos are typically what are called hot dark matter. So they move very fast, and that doesn't fit in with our ideas very well. Okay? There's a question there.
Small thought, just say 1 over r, would there have to be more mass on the outside of the galaxy to compensate for that speed?
Right, yes. So it's not falling off, so that means that there must be more mass out there.
Would it be more than in the center?
Oh, how exactly it's distributed is a little bit hard to say. But yes, there's more, but how much do you have to look in quite a bit of detail? What else? Something to make dark matter from. I don't know. What about if it were a small neutrons, lots of neutron stars out there? Would that work? Well, probably no, because that's baryonic, right? But still, we could look for little compact objects that make up so, lots of little black holes that formed from something that wasn't baryonic. Okay, these are all questions we can consider later, but I just want you to think about what could be there in the outer parts of this to make these rotation curves stay flat. Okay, so that's one piece of evidence for dark matter. And now I want to talk about another piece of evidence for dark matter, gravitational lensing. Okay? And we had a bit of this morning well, it's interesting to see that the string theorists wave their hands too. Because the idea here is general relativity is just based on the equivalence principle, right? So the observer in a box cannot distinguish between A, where a box is accelerating in space. Okay, so you've got someone inside there, it's accelerating off with uniform gravitational acceleration g, and the box here at rest in a gravitational field. Okay? So that was what Einstein suggested as his equivalence principle for GR. It didn't have to be right. So there were predictions for that, right? And one of them was that if the light beam comes in here and this thing's accelerating up there, well, it will look like the light beam is bent, right? And so that's when the box is accelerating. So now here you are sitting inside your box in a gravitational field. What do you expect? Well, here's my box, and I have a bit of light coming in at the top there. It's going to be bending in the room here. Well, that doesn't feel right, does it? I mean, really. I mean, imagine me standing with a flashlight, and the light travels over there, it bends down and hits the bottom of the door. Okay, so it does happen, but it's a really, really tiny effect. All right? A really, really tiny effect. But it's led to some predictions which we could test. So just when you're thinking about this morning, the way Melanie described this, well, she said that light, we could think of it in a sort of special relativistic way, where if light had an energy, it sort of had a mass, and so it would have a gravitational effect. But she didn't say that you actually really do have to consider general relativity in this. You have to, because if you just think of it as a special relativity thing, you actually get the angle of deflection wrong. Okay? She showed the light coming in like this and getting bent. And if all you did was think, okay, it's got a certain energy, that's related to a certain mass, so I know what force acts on it, and you were an observer looking out here, you would find that angle of deflection was wrong. Okay? You actually need the bending of the space-time by general relativity to get that angle right. So it's actually the bending of light around a massive object, that's a general relativistic thing. Okay. So we've got how much time have I got? Okay. 20 minutes. Okay. Well, let me show you something else quickly then about gravitational lensing. I'm sorry, but it's late in the afternoon, right? Pictures. I actually thought this was going to be a talk to the high school teachers, so I've got a lot of pictures. Just end the show here. So this was something that was produced the Max Planck Institute while I was there. It really should be in. Okay, it's coming, I think. So just show you a few ideas about gravitational lensing. Sorry about the German. Okay, so here's your observer. You're looking out at a star. Okay, light travels in straight lines, and we assume that light has traveled in a straight line. Okay, so now what happens here is we just ignore it for a second as you put the sun right up next to that line of sight. Okay, so we're going to put the sun right up next to the line of sight, and you can see that the position of the star hasn't changed. Okay, but the light comes in from the star and gets bent into your line of sight. Okay, so let's just stop that for a second. Okay, light from the star comes along, gets bent into your line of sight. You assume it's come in a straight line, so you see the star slightly shifted outwards from where the sun is. Okay, so this was a test that was actually done in 1919 for general relativity, measured the shift in the positions of stars relative to the sun. Well, that's kind of tricky, right, because you can't see any stars during the day, so what did they have to wait for? Right, thank you. So what this shows you is the shift in the position of the stars when the sun is there and isn't there. Okay? Lovely. So we'll carry on. You can think about things other than the sun as a gravitational lens. Okay, so now we turn back a whole galaxy into a gravitational lens. So it's got 10 to the 11 stars acting as a lens, and we're going to put a distant quasar, which is just actually the center of another galaxy, just very bright, and it's got lots of interesting things happening there. Okay, let's stop that. You don't need to worry about what the quasar is. It's a bright source of light from behind. Light travels from the quasar, gets bent around the galaxy, and you see an image out there, and you can see a second image, actually. And if you line it up just right, okay, so there's me, my gravitational lens, and some distant quasar sitting out there where Cress is, then I see him as what's called an Einstein ring. Okay? He'll be stretched out into a big round ring like that. Sorry. Okay, so this is something that's not quite lined up. What you see here is a galaxy. The big bright thing at the center is just the center of the galaxy, which is the lens. Okay, but you can see these 4 other spots, which are lensed images of one single quasar off in the distance. Just thinking back to the spectra, how do we know that these 4 images are the same quasar? You're a spectroscopy man.
Yeah, you look at the spectral signature.
Exactly. The spectra are identical. They have exactly the same redshift. They have everything is identical about them, so that you know that they're the same thing, right? Okay, so I'm going to make an Einstein ring from the quasar. And this is a real observation, actually, of an Einstein ring foreground thing. And you see it at many different wavelengths, which is nice, confirming evidence that it is gravitational lensing. Okay, now I've just turned that lens into a whole cluster of galaxies, so each galaxy with its 100 billion stars, making a big cluster. So what have we got? Cluster as lens, distant galaxy, okay, being bent. We see 2 images at the moment that are highly distorted, okay? And that's what I showed you earlier, right? Here's some foreground cluster, and here is a distant galaxy that has been lensed by the foreground cluster, okay? So what has all this got to do with fundamental physics? Well, if you look at how those things are distorted, you can measure the mass of the thing in front here. Okay, we can look at how much light there is, and we can figure out that there's much, much more mass there. Okay, so we know that there's a lot of dark matter in the area of the cluster of galaxies, and in fact, we don't only use these kind of strong distortions. You can use what's called weak lensing. So you basically use a whole selection of galaxies in the region of that cluster of galaxies, and you look at very slight distortions of them to measure the mass of the cluster of galaxies. Okay. So I think that's the end of that. Let's go back to Are there questions about gravitational lensing? I'll just have to step through. Yes, that's right. Oh, why don't you ask me afterwards? It's just a solution to the lensing equation will automatically produce an odd number. Yes, the fifth one is very faint. Yeah. So you've seen this. Here's the observer. There's something that's distorting the space-time, and the light's getting bent around there, and you project back to with. So what's wrong with this diagram? Okay, I just didn't look very carefully, downloaded some diagram from the internet. There's something wrong with it. Okay, so here's the quasar light being bent into your line of sight. But of course, what you see is you infer that the light came straight, right? But they've bent this diagram down like this. Okay, bent this line down. This should be a straight line that comes from Earth because it's where you see something to be. All right? So, be careful about what you download from the internet. All right, so there's the evidence for dark matter too. A cluster of galaxies acts as a lens, distorting background images of galaxies. Mass in the environment of the cluster can be measured from the amount of distortion, and we get vastly more mass than that inferred from the starlight. Okay, there are those background distortions. So I've heard people say in talks, this is a question for GR people, I've heard people say in talks that GR is not tested on large scales. This looks like a test of GR on large scales. Weak fields, but large scales. Yeah, well, don't get, that's getting pretty large, right? So certainly if you want to say, oh, but we don't understand, we haven't tested gravity on scales of galaxies where we infer dark matter, then that's wrong, right? Because, or maybe there's something aspects of it that we haven't tested. I don't know. That's an interesting question to me. All right, so here's the promised evidence that the dark matter is not baryonic. Okay. So I said that the early universe was really, really hot, just like the inside of the star, and so we could have nuclear fusion, hydrogen turning into helium. Okay? And it produces a few other light elements along the way. This is quite hard to see. Okay. These lines here are the predicted amounts of, in this case, helium-4, helium-3, deuterium, and lithium-7 that would have been produced in the early universe during that Big Bang nucleosynthesis time. Okay, so those are the predicted amounts. Okay, that's the amount. So what's on this scale here? It's the baryonic density. Okay, so you can see that the amount of those light elements that you predict is a very strong function of how much baryons there are in the universe. Okay, so for example, as the baryon density goes up, you produce less and less deuterium. Okay? So what can you do? You can go out and look in the universe, do some of these horrible, messy astronomy observations to establish how much primordial deuterium there is in the universe. And the line that you produce comes across here. Okay? So if you just looked at the deuterium, you would drop down here and determine a baryonic density. Okay? Then you could say, all right, well, we've made predictions over 10 orders of magnitude. Is this consistent with the other things? Okay, unfortunately, you can't see the helium line, but yes. Okay, have a look at the green line. Helium-3 fits exactly with the deuterium. Okay, have a look at the lithium, fits exactly. So we have a very, very strong constraint on the amount of baryons in the universe. You can say, well, is there enough baryonic matter to make up all that dark matter that you saw in clusters of galaxies and everything? And no. Absolutely not. Not enough baryons at all. Okay, so Peter's in the room, and I know he's going to talk about type 1a supernova. Is that right? Okay, so let me just... I think that's where I'm going to stop around there. But what I'm going to do is just say something about dark energy, because you can't possibly end this without knowing that there's evidence for dark energy, and you're going to give all the other... these are the kind of pictures part, which will motivate you to do the math part. Is that right? Okay. So let me finish with the evidence for dark energy. And this is just one piece. There's another piece that will come later when I talk more about the CMB. Okay. And here's the idea. Is that you go and you look at type 1a supernova. Does anyone know what a type 1a supernova is? Quite distinct from that core collapse supernova thing that I mentioned earlier, which was the end point of stellar evolution. A type 1a supernova is when you have a binary system where one star is dumping material onto a degenerate, usually a white dwarf. And eventually it triggers a thermonuclear runaway, which produces this incredibly bright thing. Okay, can be just as bright. One supernova can be just as bright as a whole galaxy. Okay, the important thing is that by looking at the spectra, you can tell intrinsically how bright it is. Okay, so you know how much energy per second that thing is putting out. So if you know how intrinsically bright it is, okay, and you can measure how bright it looks, well, then you can get the distance, right? I mean, if you just thought of a flux of something is going to be the luminosity over 4 pi, the distance to the thing squared. Okay, and the way astronomers write that is to say that how bright it looks, okay, minus how bright it really is equal to log d over 10 parsecs. Okay, so that's, I'm just showing you that because that's what's plotted over there is the little m. Okay, so what we assume is that we really know big M, which is how bright it really is. That's how bright it looks, and it's just related by the distance. And this distance is a function of the cosmological parameters. Okay, omega m, omega lambda. Okay, so I don't know if you did anything like that in your cosmology lectures, but the distances to the things would be a function of the cosmological parameters. So how that little m depends on redshift, which you know to be just an estimate of distance. Okay, well, related to the distance. So as you go further out in larger redshifts, you go to further distances, and how that depends on, how bright it looks depends on the distance. It'll look different for different combinations of the cosmological parameters. And I'm sorry, you really can't see these on here. Maybe I should just draw the diagram over here for you. I don't know if maybe the lights should go off or something. So basically it looks something like this. And all the supernovas sit along one line like this, which is sort of the important thing about that line is omega lambda is greater than 0. Okay, so here you can look at the kind of constraints that are implied, and we've got omega matter plotted against omega lambda, and we require those brightnesses, for those brightnesses to be what they are, and we're working in that standard cosmological model we talked about, then those are the constraints that are implied. Okay, and we'll say much more about that. But here's just a summary of the ideas so far. Okay, so then in the next lecture, I'll come back to look at these kind of main ideas and say, all right, well, what can we actually do to go beyond this? So what I'd like you to do is to think, first of all, about what you haven't understood so far, but you can also start thinking about, well, if I wanted to go beyond this, what would we do? Okay, what big questions do we have? And I don't know, we're having a lecture later. If you could just write any questions down you have for me and just give them to me at the end of the next lecture or something, that I can put them into tomorrow's talk. Okay, I'll answer them for you. So just write them down, and we don't have to have the big stand-up in class and everything. So, and then I'll answer those tomorrow. Okay, so that's just a reminder. So if you've got nothing to do right now, you can try and remember what each picture is. Okay, I'll stop there. No. Don't go ahead. If you've got questions now, it's just, it's a bit intimidating maybe.
So part of our goal is not to be intimidated by each other's presence. We should ask questions because they may be a benefit to others than you. So please ask some questions.
You see?
She made a comment
No, that's what I said. No, that was a flippant throwaway comment about if we look out and we look at all the galaxies and they're moving away from us. Okay, your first thought might be, wow, that's amazing. We're at the middle of the universe and everything's moving away from us. But that would just be, we've got a much better way of thinking of it, and that's in terms of the expanding space, right? So, for example, if I wanted to make a one-dimensional universe here, and I just put out an elastic band that stretched off to infinity, and I marked two little galaxies on it here, okay, then as the space expanded, so I marked 2 galaxies, more galaxies, so all of the galaxies that was not mine would be moving away from me. Okay, but it's not that we're at the center or anything. This is an infinite piece of stuff. It's just everything, the whole space is expanding, and so that's why all the galaxies look like they're going away from us.
It's true for every galaxy.
Yes.
They all see all
Yes, it doesn't matter which galaxy you're sitting on. Everything. So sometimes it's quite hard to picture this expansion stuff. So it's always helpful to start with what would it look like in 1D? What would it look like if we were on a big flat sheet? Okay, so we have a sort of infinite sheet extending off, and we put a couple of galaxies on there, and you put yourself on one of the galaxies. What would it look like later once that space is expanded? Okay.
And a rubber balloon is the most useful
Yes.
thing. You bring a balloon, you put some dots on it, you blow it up, you want all the dots move away from each other. No particular dot is the center.
And they'll immediately ask you, what is our universe expanding into? Because the balloon is expanding into something, right?
Sure.
Okay. What is the balloon expanding into?
Well, I think another nice point about this balloon idea is that Hubble's law, for example, is not so much a feature of the underlying theory of gravity, it's actually a feature of geometry. So when you take a balloon, you blow it up and you see the galaxies all moving away from each other. That's actually not so much a function of the theory of gravity, it's actually just a function of the geometry that you're using to describe the surface on which the galaxies are sitting. So it's actually independent of your chosen theory of gravity.
Well, just a comment to clarify to people who don't know. There's not every single galaxy that's receding from us. It's only the ones that are reasonably distant, because there are some that are in fact heading towards us that belong to our local group. Like the Andromeda galaxy you showed, that's one there. It's approaching us about 200 kilometers every second.
Yeah, that is the one. There are 3 or 4 galaxies out of the billions. So if we go back to this picture here, for example, okay, I'll look out and the space is expanding, so everything will be getting further away from me. But actually, if I go and look inside that cluster of galaxies, okay, everything will have fallen together. They'll have velocities like this. Okay, so within that cluster of galaxies, they'll all be moving around with velocities that are actually sort of decoupled from the expansion velocities. Okay, so this is what you're describing. We have a galaxy which is near to us. Okay, distant galaxies will be expanding away. Near to us, this one will be falling towards us.